For I am a man of a constant sorrow. Okay, so what we're looking at here is the beginning of Unit 4, and what we're going to be talking about are vectors. Now, we've previously talked about vectors a little bit this year when we've had ideas of displacements, velocities, and accelerations, and we designate vectors as having a little arrow over our head here. And this is an X. How's that so hard? Now, we've previously talked about scalars as a quantity defined and described only by the magnitude. And by magnitude, we mean the size and the unit of something, okay? So it's just like how big it is. It's 5 kilograms, so 5 being the magnitude, kilograms being the unit. That's a scalar quantity, so it's an amount. A vector, though, is completely described by two things. It's the magnitude, but it is also needing a direction, okay? If we think back to our ideas of speeds versus velocities, I could say that you're moving at 10 miles per hour. That's a scalar. It's a speed. But if I say you're moving 10 miles per hour north, south, east, west, upwards into the air, now we've given you a magnitude, 10 miles per hour, and we've given you a direction, north, south, east, west. West? So this will give us a actual vector here, okay? And these vectors, we care about the magnitude and the direction. Now what we're going to be looking at here are a few different ways in this unit to properly describe vectors and how we can do that. And we're going to do things graphically a little bit in this class. Normally we do a little bit more graphically than in normal years, but due to COVID and things kind of being weird, it's kind of not as easy to get everybody rulers and to start touching a bunch of things and sharing a bunch of things. So we're going to try to stay away from that. And we're going to look at things a little bit more from the mathematical perspective this year, which we always do, but just we'll focus on this a little bit more. Okay. Now there are many ways that we can define vectors, but the three we're going to look at this year are polar notation, rectangular notation, and unit vector notation here. And let's actually start with rectangular notation. Let's look at the second one first. Now, rectangular notation, it's got a really cool name. It's like rectangular notation. Sounds like a lot of rectangles are going to happen here. But this is just what you're already used to in your math classes. These are just x, comma, y amounts, okay? We really just think about rectangular notation as x, comma, y. Where the x amount is the amount going in the x-axis, so is it going left or right, and the y amount is going up or down, okay? So if we had some vector here, we would simply just write this as x, comma, y, okay? And specifically, if we were looking at something like velocity, it'd be like the velocity in the x direction, the velocity in the y direction. But they are really just x, comma, y amounts that we could put in parentheses for this. On other ways we can think about things, if we go to unit vector notation, so let's actually look at the last, what we'll do for unit vector notation is we're still going to look at things as x and y's and possibly z's if we're in 3 dimensions. But instead of writing it like x, comma, y, we're going to think about doing x plus y. And instead of using x, y, and sometimes z, we're going to use the letters I, J, and K. Essentially, the way we can think about this is that X, Y, and Z can be thought of as I hat, J hat, and K hat. And what this simply represents is being in the X, Y, or Z direction. Okay? Now, the way we'll write this out is our full vector will be an amount, it'll be some number, in the I hat direction. So maybe it'll be like 7 in the I hat direction plus, and then, I don't know, pick another number. Let's go with 4 in the J hat direction. If you wanted to convert this unit vector into rectangular, this would just be 7, comma, 4. So it's very similar to the rectangular notation, except we're adding each of the component directions I, J, K instead of just saying X, Y, Z. Okay, so it's a little different, but very much the same. The one that is a little stranger is actually polar notation. Polar notation deals with having the actual length of our resultant vector, which we'll talk about how to get that a little bit later, as well as the actual direction it is pointing. So if we go over here and we take a look at a grid, if I take a vector and I point it up like this, well, this vector, it has some length, okay? It has some length. We'll just call it length v for a vector. Now, this vector is also pointing in a direction. We can see here that it's pointing kind of up and to the left, but what is the exact direction it's pointing? Well, the angle we want to figure out the direction it's pointing goes from the x-axis, so our positive x-axis is right here. It goes from this positive x-axis all the way around until it strikes that vector. That is some angle theta, okay? It's some angle there. This is the angle that defines the direction of the vector. So v is the size of this vector, and the angle theta is the direction. So whenever we go and write this out, we would write this as v, comma, theta. This has a size, and this has a direction, okay? This polar notation is very powerful because we immediately know that we have a vector, we have a size, and a direction, and we know what those directions are. It's very nice whenever we're trying to graph things out. The rectangular and unit vector notation, they're not as nice when you're trying to draw things out graphically because you don't know an angle. You just know x's and y's. You're just kind of moving things around. Rectangular and unit vector notation are very nice mathematically because we can add things in the x-axis and the y-axis together very easily. It's what you've been doing for years with the number line. Whereas the polar notation, it doesn't exactly work super easily when you're just trying to add things together. You actually have to break things back into the other methods. It's important to recognize, though, that if you are using polar notation, you do need to be a little careful. If you have a vector that's coming down like this, it is very important to remember that you want this entire angle here. So if you're only given that this angle in blue is, let's say, 40 degrees, but you want to get the entire angle in green, you cannot just say that this is some vector v comma 40. You can't do that. That's not going to work. You need to go all the way around from the x-axis, which means that it's very important for us to remember that going halfway on a circle is 180 degrees. Going a fourth of the way on the circle is 90 degrees. Because what we're able to do now is say that 180 plus the extra 40 that we have here would give us an angle of 220 degrees on this vector. And that 220 is actually what we're looking for. Okay. It's also possible, if you wanted to, if you have polar notation, you can actually give a vector in terms of a negative angle. Let's say I know that here's some vector v, and I know this angle here is 20. I could write this in two ways. I could write this originally as the vector length of v, comma, and then if I go all the way around, this would bring me to 340, because I know one complete circle is 360 degrees. Thank you for teaching me that, Tony Hawk. And 360 minus 20 would only give me 340. Okay, so that's one way to write it. The other way I could write it is I could say v, comma, and then minus 20, because when you're going clockwise around the circle, those are negative angles. We think mathematically that counterclockwise are positive angle measurements, okay? So the 340 is what we traditionally use. That's what we traditionally like. But if you do put negative 20, you're not wrong, okay? So it's a kind of neat thing about physics. So these are the three ways that we're going to be talking about vectors and thinking about them throughout this unit. We've got polar notation, rectangular notation, and unit vector notation. We'll see how they all interrelate and how we can go from one to the other as this unit progresses. But to do that, we will need to make use of the wisest and most sage chieftain in all the land, Chief Sokotoa. And we're going to see how to use some trig in just a little bit in our next video. So until then, adios and take it easy.